let's take a look at the comparison theorem. The comparison theorem is a theorem we could use to determine whether improper intervals converge or diverge. Okay? Suppose that f and g are continuous functions with f of x being greater than or equal to g of x, which is greater than or equal to 0, for all x greater than or equal to a. So this picture on the left here indicates what we're trying to talk about. We could see that a is this important point, and we're going off to positive infinity. We can see that f is always going to be bigger than or equal to g as for all values of x that are greater than a. Okay. So what the comparison theorem does is it sort of relates the convergence of one integral f with the convergence of another integral g. So let's say that the integral from a to infinity of f of x dx converges. Then this is going to imply that the integral as from a to infinity g of x dx, this also converges. If we take a look at this picture on the left again, we're basically saying that the area under f, this whole area here, is finite. And because the area under g is actually smaller, that means that the area under g also needs to be finite. All right? So let's look at the other case. The other case is that the integral from a to infinity of g of x dx, let's say this diverges. If that's the case, then that means that the integral as x goes from a to infinity of f of x dx, this one diverges as well. So that makes sense for us because if you look at the area under g, this area here, let's pretend that's some infinite number. Then since f is actually bigger than g, the area under f also has to be infinite, which means that's going to diverge as well. Okay, so let's take a look at an example, example 8, and we'll see how this guy works. Okay, so the first thing we're going to do is we're going to take a look at our integral. We're going to go from 0 to positive infinity. We're going to integrate this function e to the negative x squared. So that's this function over here in red. Okay, and the very first thing we're going to do is we're just going to cut it at 1. So I'm going to draw a little line here at 1 like this. And what I want you to notice is I want you to notice this area to the left. So all this area right here. All this area right here to the left. In other words, from 0 to 1. This area is finite. Right? I mean, it doesn't go off to infinity. It's a bounded type thing. So I guess what I'm trying to say is we know the integral from 0 to 1 of e to the negative x squared dx is finite. So what we're really trying to figure out is, what about the area going from 1 to positive infinity? So what we're going to do is we are going to compare the integral from 1 to infinity e to the negative x squared dx. We're going to compare it with another integral, the integral from 1 to infinity e to the negative x dx. So this second integral, this second function right here, this is represented by this blue curve. Okay, so we can see that the area under the blue curve is going to be greater than the area under the red curve over here. So we want to basically check, does this converge? All right. So we're left with calculating this integral. I suppose you should actually show that the blue curve is actually above the red curve. We're going to just assume that's true for now and calculate this simpler integral over here. I want to point out that this integral actually is impossible to integrate, so we're almost forced to use a comparison theorem. So let's see how that works. So we have the integral from 1 to infinity e to the negative x dx like this. And what we're going to do is we're going to use u substitution. So we're going to let u equal to negative x, then du is equal to negative dx. And, when x is equal to infinity, that's going to mean that u is equal to negative infinity. And when x is equal to 1, that means that u is equal to negative 1. So our integral is going to become the integral from negative 1 to negative infinity e to the u du. And we're going to pull that negative outside, this negative that comes from the dx part. All right. We know that we can interchange the limits of integration, but then that's going to change this negative in front to a positive. So this is going to become the integral from negative infinity to negative 1 e to the u du. And this is a type 1 integral, so we need to express that as a limit. So we're going to have the limit as t approaches negative infinity of the integral from t to 1, negative 1, e to the u du. All right, so we need to evaluate that. So the antiderivative of e to the u is just e to the u. And we're going to have the limit as t goes to negative infinity, e to the u evaluated from t to negative 1. So substituting in the negative 1, I'm going to get e to the negative 1. And then we subtract the limit as t goes to negative infinity, e to the t. Now we know that as t goes to negative infinity, e to the negative infinity goes to 0. So in the end, we just simply get e to the negative 1. This is a finite number, which means the integral converges. Okay. So by the comparison test, the integral from 1 to infinity e to the negative x squared dx also converges. All right. Earlier, I had said that we really need to make sure that this blue graph is in fact above this red graph. So why don't we discuss that? I probably should have discussed that earlier. So I'm trying to say for x greater than 1, e to the negative x squared is actually less than e to the negative x. So how can we see that that's true? We could take natural log of both sides. So when I take natural log of both sides, I get something that looks like this. Remember, natural log is 1 to 1, so this is totally allowed. I can use the third law of logarithms to bring the power down in front. We get negative x squared is less than negative x. If I multiply both sides by -1, then that says that x squared is actually greater than x. Remember, when you multiply by a negative number, you have to switch the direction of the inequality, and this is obviously true for x greater than 1, right? I mean, if you looked at the graph, x squared looks like this, y is equal to x squared, and y is equal to x looks like this. And we can see that for values of x that are greater than 1, x squared is clearly above x. Okay, so we should have showed this before using the comparison test. I wanted to integrate first and then show you that this relationship was true after. All right, everybody, take care.